And now let us see how to characterize the supreme. So the next topic is the characterization of the supremum and of the infimum. And so here we start with a proposition. That says the following. The idea of characterization is to give a sort of alternative definition that it is more comfortable to be used, to be applied. So here we have a subset A of R, which is upper bounded, and then you have that psi is the supremum of A if and only if. First, we know that psi is the minimum of the upper bounds, so psi is an upper bound of A This is easy. This means that for every x in A, we know that psi is not smaller than x. And second is the following. So I write it here and then I will explain. For every epsilon larger than 0, there exists an x in A such that x is larger, strictly larger than psi minus epsilon. This means the following. This is very important to be understood, so I ask you to stop the video if you don't understand this point. Here you have your set A, as usual, and the supremum here is psi. This is psi, the supreme. Now, here there is for every epsilon larger than 0. And then here I will say that there is an x larger than psi minus epsilon. So psi minus epsilon means that we move a bit psi towards the left. So there will be a point here, psi minus epsilon. So here is psi, here is psi minus epsilon. By subtracting this positive quantity epsilon, I move psi a bit on the left-hand side on the real line. Okay, this is the main point. Now, I'm telling that for every epsilon larger than 0, which means regardless of how much I move psi towards the left, there exists an element of the set A which lies on the right-hand side of psi minus epsilon, for instance, here. So if I am leftwards with respect to the supremum, then there is an element of the set that falls here. And for instance, here, sorry, I changed color because the same color is confusing. Sorry. And here is psi. So there is, for instance, green, an element x that is here, which is strictly larger than psi minus epsilon. So, or if you want, in a perfectly equivalent way, this means that for every lambda less than psi, there is an x in A such that x is larger than lambda. So it is exactly the same thing, but instead of introducing this epsilon, we just say for every lambda which is smaller than psi, so which lies leftward with respect to psi. Okay, it is completely equivalent. What is the advantage of introducing epsilon? Conceptually, there is no advantage. The only fact is that we will deal a lot with the epsilon in the following of the course. So we may find it convenient to do it properly now. Okay? So this is the second definition. And so if you want, I can give you a proof of this, but I don't want to give you a proof. I just want you to understand the point here. This is the most important fact. Proof. Left as an exercise. It is a sort of boring proof, but it is more important to understand what happens. And so to notice that point 1 embodies the fact that the sup is an upper bound. If you want, this is the easy part. The second point in the characterization I gave is simply that the sup is the lowest upper bound. The sup is the lowest upper bound means exactly that if we consider a lower number than the upper bound, then it cannot be an upper bound. There is an element of the set that exceeds this sort of shifted towards the left upper bound. So this is very important. And the message that we have from here is that the sup is somewhat attached, and the exact mathematical word is adherent. To the set. So this is the main fact. And what does adherent means? It means that if my set A, of which I want to compute the sup, is for instance this one, the sup is not here. The sup is not here. So there is no space left, there is no gap left between the set and the sup. So this is a gap. You cannot have a gap. So the sup must be here. The sup is somewhat adherent to the set. Okay? So think of it and then try to solve these exercises. This is compute maximum, minimum, supremum, and infimum of the following sets. So some easy exercises, but you have to reason a bit. The first is A is equal to the inverse the set of the inverses of the natural numbers except 0, of course, that has no inverse. Second, the union for n going from 1 to plus infinity minus 1 over n, 1 over n. This is a strange notation, but what does it mean? It means that you consider all these sets when n varies from 1 to infinity, so in all naturals, and you make the union of all of them. So this is minus 1, 1, that corresponds to n equal to 1. And then union minus 1/2, 1/2, that corresponds to n equal to 2. And then union minus 1/3, 1/3, n equal to 3, and so on and so on. And so you are asked to perform the union of all of them. This union is very easy. Third, the same with the intersection, but this time of closed intervals. And you will see what happens. Okay? So these exercises are of basically they are made of 2 steps. The first step consists in understand what kind of sets are they, and once you write down the set, it is very easy to write down max, min, supremum, and infimum. Okay? Good. And this is what is sufficient to us in order to get acquainted with the notion of supremum and of infimum. Remember that it is very important. So now with these notions we can prove something that is quite important, which is the density of rationals. In reals. What is the meaning of this strange title? So remember that we introduced reals as a completion of the rational, with respect to the fact that there are holes in rationals, and we just filled all gaping rationals in order to obtain the reals. Okay, this was our main concern. So, however, irrationals are really a lot of number, much more than the rationals, but if you remember well, I also told you that reals are uncountable, rationals are countable. So reals are much more than rationals, but rationals are dense. What does it mean? It means that for every, so given a couple, whatever couple of reals, there is always a rational that falls, a rational that falls between the 2 numbers of the couple. This is what we will prove here, and want to tell you what do I mean. I mean the following. You consider real here x, another here real here y, and so you find a z here, which is rational, that falls and falls between x and y. Of course, if there is always a third number there is always a fourth, because I consider x and z, and here between x and z there is z1, and between z1 and z, z2, and so on and so on. So, as a simple consequence, there always are infinitely many rationals between the elements of the couple, of the chosen couple, or reals. This is an extremely simple consequence, and another formulation can be, so density can be summarized by stating that inside every real interval there always fall infinitely many rationals. Very easy. And now let us prove this property. The first step is the following. A theorem which is known as Archimedes Property. That seems to be very, very stupid, but again I want to show you that in the analysis everything must be proven. And this is the Archimedes property. You consider two arbitrary real numbers, x and y, with y strictly larger than x. So the situation, as usual, is the following. Here you have 0, x, and y. And Archimedes property says that there always exists a natural number n such that n times x is larger than y. So it doesn't matter how much x is small with respect to y, but if you perform a sufficiently number of steps equal to x, sooner or later you will overcome y. Okay, this has to be proven. And the proof is really non-trivial. In particular, it is a proof by contradiction that says the following. So we argue by contradiction, and we say, suppose that it is not true that there exists a natural number n such that n times x is larger than y. So this means that we deny this proposition. We obtain that for every n natural, we have nx less or equal y. This means that the set A equal to all multiples of x, or natural multiples of x, is upper bounded. Why is it upper bounded? Because every nx is upper bounded by y. By y. So this means that the supremum psi of A is less than infinity. Okay, now consider the characterization of the soup that we gave some minutes ago. For every lambda less than psi, there is an element, let me call it eta, in A, such that eta is larger than lambda. But what are the elements of A? Are n of x, so there exists an n natural, so let me call it n bar because it is a specific n, so I help this idea of specific n by adding this bar, such that eta, which is n bar x, is larger than lambda, and I choose lambda to be psi minus x. Okay? I can use whatever lambda less than psi, and I use lambda equal to psi minus x. So now what I use of this inequality is n bar x larger than psi minus x. And so I take this x here, I bring it to the other side of the inequality, and I end up with n bar plus 1 x larger than psi. But this is absurd because n bar plus 1 belongs to A. Psi is the supremum of A. So here we constructed an element of A that exceeds the supremum of A, and this is absurd. No element of A can exceed the supremum of A. This is the end of the proof. The absurd is here. We suppose that it is not true that blah blah blah, then blah 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 is true, since we got to an absurd. And now we go to the last theorem, the density of rationals in reals, which is the following. So let A be in R with A less than B, and then there exists a Z in the open interval AB, which means that Z lies strictly between A and B, such that Z is rational. Proof is very simple by using Archimedes property. So there exists a natural number such that n times b minus a, which is positive because of this hypothesis, is larger than 1. So we compare 1 and b minus a and we apply Archimedes property. Okay? So this means that nb minus na is larger than 1. So picture, here you have na, here you have nb, and this interval is larger than 1. And now we have that here there must fall an integer, because the interval between the integers, between the subsequent integers, is always 1. So since inside every interval larger than 1 there must be an integer there exists an integer m lying in MA MB such that we have NA less than M less than NB, so A less than N over N less than B. And of course, M over M is a ratio between two integers, so it belongs to Q, and then the proof is complete. Okay, I stop here again, and then we move to the next